Okay, so what we've been able to establish the other time is that for the first language, which is this language is a regular expression, while this other language is a context-free grammar. That is why for the first question, are they alike? No, those two languages are different. So in mathematics, they are the same, but in computer science, they are different. This second language takes something more to solve than the first language. That's why they are different. Now, let's continue. Of course, you guys are familiar with this table. You've done this when you guys were talking about grammar and grammar types. So I just want to show it to you again. Now, for our previous lectures, the design and everything, all the grammar we've considered is just the regular grammar, and all the strings we've considered are just the regular language, which is over here. That's all we've done so far. So we're taking it a step higher. We are going here. We are going to context-free grammars and context-free language. So we'll be working with the pushdown automaton to see how the pushdown automaton effectively solves a problem like the one I gave to you earlier. And again, just to I don't know, you guys will have talked about this, but just to refresh your memory, this is the language we're trying to solve the other time. This is the string type, the regular grammar. Now, this is what I was trying to show to you in the example, where I told that you need a counter and a register. For some other some higher grammar, like the context-free grammar, you need something higher to solve them. Of course, you need the linearly bounded automaton to solve this, and you will need the Turing machine to solve this, which is the type 0 unrestricted grammar. So, to the pushdown automaton back again. So, what is the pushdown automaton? A pushdown automaton provides a way to implement a context-free grammar. So, it is basically your normal finite state machine plus a stack. You see it. Now, a pushdown automaton has three components. First is an input tape. Well, of course, your input tape is still your inputs alphabet, just where it takes in its inputs. Then you have a control unit. The control unit is just your normal FSC. That's what we're saying there. Your normal finite state automaton that moves from state to state. Then you have a stack of infinite size. Now, diagrammatically, let's look at. Okay, I've not got to the diagram. Now, the stack performs three operations. First is the push, second is pop, the third is in. But actually, I'm going to take out this third operation because for your level you don't need it. Just let's work with the push and the pop operation, which is, of course, in a stack. You know that if you push, you want to stack over the stack, and when you pop, you take out the topmost element from the stack. So a PD may or may not read an input symbol, but it has to read the top element of the stack in every transition. No matter what, it must read the top element of the stack. So here is an example of a pushdown automaton. This is the input tape, like I told you. This is the control system, which is the normal finite state automaton, and here is the stack. It keeps stacking till it gets to the final state. So now, generally, this is the accepted operation of a pushdown automaton. Now, if you have a queue, okay, let's say this is Q1 and this is Q2 or Q0 going to Q1, either way, you're supposed to have three things on top of it. First is the input. This is what you want to read. A is what you want to read. Now, B is what is on top of the stack, while C is the operation. Now, you see, when I'm performing some example, you understand. Now, this can be either the push or the pop. Forget that it's only push that is written here. Is this supposed to be stack operation actually? Instead of having just the push symbol, you're supposed to have stack operation here. Because you can either push or you pop. Now, what is the formal description of a finite automaton? A finite automaton, let's say a pushdown automaton. A pushdown automaton has 7 tuples. We have the queue, which is the finite number of states. We have the input alphabets. We have the stack symbols. We have the transition function, so that once you take in queue, and once you have queue, which is the state, and you can read an alphabet from the input tape. This is the alphabet in the input tape. Union empty. Don't forget something that I said earlier on. We said a pushdown automaton may or may not read in an input. That is what this is trying to cater for. This. So just in case if you are not reading in an input, you want to read an empty string. This is what this part means. So, but all the same, this is an input. Either if it's part of your alphabet or you're reading in the empty string. This part is just the input. Now, and you have a stack. Then you're supposed to go to another state and you're supposed to perform a stack operation. That is what this means. Now, Q naught is the initial state, which such that Q naught is part of the state. You know that already. I is the initial stack symbol. Please note that I is the initial stack symbol, and I is part of S. F is a set of accepted states, so that of course you can have more than one final state in pushdown automaton. So let's move on. Now, for the example I gave to you the other time, now let's try. This is I'll still try and solve it in JFlap, but there's a bit of difference. That's why I said general operation and JFlap operation. You see, but the difference is not so much. The difference is that generally you don't know the machine you're going to use, you don't know the your testing environment, or you don't know how you want to deploy it. So there are some testing environments, or there are some tools that will not automatically initiate this part for you. This part, you see, this part is when you're inputting the initial stack symbol. That's what this part does. Now let's start. Let me break down. We want to pass L2 so that we have A raised power n and B raised power n, so that n is greater than or equals to 0. That is clear. Now, n is greater than or equals to 0 means that we can pass an empty string or lambda. Now that's catered for A. That is why Q1 is also a final state, because we can pass lambda. Now, but to pass A raised less n or B raised power n for a pushdown automaton, the first thing I think I have to do this together with this. Let me take this out. So let's start from here. Okay, now this is the transition table. This is a transition table for finite pushdown automaton. I don't know why I keep saying finite automaton. This is actually a pushdown automaton. Now this is the input string that we want to read. This is the stack. At this point, the stack is empty. Like I said, for generally, let's assume that the stack is not empty. But in JFlap not automatically puts the empty string, put the initial stack symbol for you. But other environments may not necessarily put it. But so let's assume that we're using other environment. We're not using JFlap for now. Just let's assume we're using another environment. So now, this stack is empty. We don't have a next state. Now, let's go to the next second operation. Now, for the second operation, first thing we want to do is that we want to first initialize the stack. We want to pass the initial stack symbol into the stack. To do that, don't forget what I said. This first part here is the input element. This is the top of the stack, and this is your operation. Now, what this means is that we want to push in this symbol, this initial stack symbol. We want to push it in onto the stack. So everything is still empty now. So our state, which state are we? We are state Q1. We want to read in this input. So once we read in that, input. Now, our stack. What are we passing to the stack? We are passing this $sign, this initial stack symbol. So let's put in the initial stack symbol. Which is this $sign. So once we have that, which state are we going to? We are going to state Q2. So that's what happens over here. So with this, we've initiated our stack. That's what that does. Now, let's continue. So I will be fast. Let me just copy this and paste it. So we then do number. So for the third operation, we are at state Q2. Don't forget, from this example, we are at state Q2 now. This part we've initialized the stack already at this point. So we're already at state Q2. Now at state Q2, what is on top of this? What it says is that if we have two possible operations. Firstly, if you want to read in 0 or you want to read in 1. If you want to read in 0 and the top of the stack is empty, push 0. Now, let's see. What is the top of the stack? The top of the stack is, this is the top of the stack. This is our last operation. Let me take that so it won't confuse you here. These are our last operation. So this is the top of the stack. So the top of the stack is still empty. This is just the initial start symbol, don't forget. So the top of the stack is still empty. So what are we supposed to do? From this, we're supposed to stack in 0. So we're supposed to having $sign, which is which was supposed to having $sign over here, and we're supposed to have 0 over here. So we've done that. So once we do that, where are we supposed to go? We're supposed to remain on state Q2. So that's why we're on state Q2 over here. Now let's continue again. If we are on state Q2 and what have we read? We've read in 0. Let's at this point we read in this. Let me put it in bold so we can see what we read and what we've not read. Let me change the color of this one too, so we can see what we've read and what we've not read. So we've read this. Now let's continue. So the next thing we are supposed to read is this second 0 over here. So let me bold in it so we can see. So we're supposed to read in this second 0 over here. So from the diagram, if you're on state Q2, we're on state Q2. If you're on state Q2 and you want to read in 0 and the top of the stack, what is top of the stack? The top of our stack here is what? Is 0. We already have a 0 on top here. So this is top of our stack. So if the top of the stack is 0, now what are we supposed to do? We're supposed to push in 0 again. So we're going to have $sign. We have the first 0 that we had first time, and now we're pushing in another 0. So which state are we going to? We're still going to remain on state Q2 based on what we have over here. Now let's continue again. So having done this, let's go to the next step. So we're on state Q2, and this is still our input string that we are reading. Now we want to read in this one. This one. This is what we want to read in this one. What's on top of our stack? 0. So if you have a 0 on top of the stack and want to read 1, we have a 0 on top of the stack and want to read now. What should we do? This symbol means we should pop. This means pop. Now let's pop. If you pop, what are we going to get? We're going to take out this last 0. So that's going to be $sign. That's going to be $sign 0. So which state are we going to go to? We're going to go to state Q3. Now then the next one, that's number 6 now. So we are on state Q3 and we want to read in our input again, and this time we are reading the very last element. Now if from what we have here, we are on state Q3. If the top of the stack is 0 and you want to read in 0, pop. So top of the stack is 0. I want to read in 1. What I'm going to do? We're going to pop this 0. So what I'm going to have? I'm just going to have our $sign, and what we're going to go to remain on state Q3, just like we have in this diagram. So finally, the seventh stage. So we're on state Q3, and if we've already read our everything, so now at this point you've already read what you are supposed to read, but you want to take out the initial stack symbol that you initiated here. So what are we reading in? We are reading in empty E, just like we have here. So if you are having E,